Hey there, this is a video on this little header library I wrote to experiment with how much you could do in just C, and then started to break out into using a few non-C features in order to see like how far I could go with getting the API I wanted. This was not designed to actually be used in any serious capacity, so please do not. There is a GitHub link in the description. It's technically FOSS under the LGPL v3 license. The original idea was, can I get type-safe containers in just C using macros? And the answer is, for the most part, yes. However, in order to get all the way, I had to fall back on using function overloading from C++, along with a few other features. Let's go over the non-C features that are being used really quickly, because that'll be pretty educational when it comes to looking at the rest of what we have here. This kind of puts stuff into context. So there are two C++ features being used: function overloading and auto. It makes some macro stuff nicer, where it seemed better to use that than there's a GNU-C extension for, it basically does the same thing as auto, but it's a GNU-C extension. It didn't quite work how I wanted it in one location, and it's just better to use a full actual feature because I'm already pulling in function overloading from C++, so why not? And we're using 4 GNU-C C++ extensions. We have statement expressions. That's used in one location, at least one location. And then we have attribute cleanup. We'll talk about that in a bit. Then we'll pound sign between comma and Vargs in a macro. That handles when a Vargs there are none. There is a C++20 thing to handle this in a different way, but I couldn't quite get it to play with what I wanted, and I was fine with this. And type of expression. So let's look a quick look at the API. We'll talk about this in a bit. Here's an example of a list of U32, and we give it a destructor. This is the attribute cleanup. This is just a macro that makes that slightly less annoying to type. And we give it a new list of U32. We can push a 0, a 1, a 2, and a 3. We have an index value here, and we remove the value at that index, and then we print out the value at index is, and then we index the list with that value. So value index 2 is 3, because originally 0, 1, 2, but then we remove that, so 0, 1, 0, 1, 2, right, because we removed that index. We have an empty line here. We'll talk about print line in a bit. I'm rather quite proud of the horrible hacks, plural, that are at play there. Here you have a map of a string and a string. So key value, we call it map. We give it a destructor, and we create a new. And here we have a key and a value. Notice they're strings. These are heap allocated strings. They can grow. We're creating from a literal. So A to first, we insert that. B to second, we insert that. C to third, we insert that. And then we look up from whether key B. Notice how the keys are actually heap allocated strings, but we're looking up by a string literal. And we get a pointer to our string value. Our value is a string, and we print that out, and we see found second, found B goes to second. We have an empty line. We have another map. This is the same sort of thing, but here we have a U32 key and an F64 value, destructor, constructor. We insert a bunch of things, and we look up by 180. We see you get 19. You can see we get 19. Now, and this is just some stuff that's showing that if we were to, I'll show some stuff with that in a minute, but that's important for some stuff. We can remove the value that's at the key 180, at which point that lookup will panic. Fail to find value for key 180. These casts are required because I'm using function overloading for hashing and equaling, which means that the compiler doesn't know what overload to use because there's like 8 to 12. I'm pulling a number at my butt. There's a bunch of overloaded functions for different numerical types, and when it's a literal, it just has no clue which one to use. It has no clue, which is a bit unfortunate. But and then here we have another example where we're using a signed 64-bit integer as our key. So now what's enabling this stuff? So here we have some defines, which are we're creating a list type, a map type, a list type, a map type, and a map type. So if here we're creating a list type of t string, and we give it a destructor, so that when we destroy the list, it knows to destroy all the strings with this destructor. Here we create a map type of string, key, and string value, and we tell it the destructor for those as well. Now this is actually required for that. Maybe it's not. I forgot. Maybe am I actually defining that? Oh no, those aren't required at all. Anyway, that's still instructive to show how this sort of thing works. You have another list type, a map type, another map type, because here's our 32, U32 to F64, and our I64 to F64 from down here. So the ways these work, here's our list. We take our T and our T destructor, and we come down through this stack of macros down into this big papa, and this defines our list. We have our head, we have our len, our capacity, and then we have a bunch of functions. So we have our new, because remember we had our list U32 new, etc. We have new with capacity, expand capacity by, and destroy, which goes through each entry and destroys it with that destructor we told it. And then here we have a little trick using function overloading to allow removing at index, this macro down here, to be able to destroy the value if you remove at index. Because we're using the list as a filter so that we know which destructor to call. Because we don't know what this destructor could be called, it's not always going to be t_destroy, right? You could name it whatever you want and then just tell the macro what it is. So we have our push, our move index, and then we have our for each, which is just a for loop over the up to len. And it does have capacity versus len. So there is a the default capacity is 0, if I remember correctly. Yeah, capacity 0. And then as you push, it will actually double in size every time you reach capacity. And you can just get your capacity in len. And that string we were talking about is actually a type def of a list of bytes. And then we have a bunch of stuff on that. And we have a bunch of macros for defining different types of equality and hashing functions. And this is a massive pain in the butt to try to debug. If anything goes wrong in here, you don't get your error in here, you get your error out here at the usage site. So I've taken to I will pre-process the file and then run it through clang format, and then build that, and then I get my compile errors, and I can go look at the preprocessed output and see quite exactly like what it's outputting. Like I said, I wouldn't use this in an actual thing, but it's fun to think about what this sort of thing would require. I'm quite proud of the map because it's quite difficult to actually find information online about how to implement proper hash maps. But I have a fairly amateurish implementation here. We have a default map capacity, a default bucket size. So if I were to lower this down to 2, and we run this, we'll talk about that in a bit. You can see as we're pushing elements into the hash map, it will grow the bucket size, depending on the number of things in there. It's very naive. Basically, if the number of items reaches the bucket count, it just doubles the bucket count and reallocates everything. You can see here we have, if we tell it to use a default bucket count of 2, and all of these we're doing more than 2 elements, right? It reallocates and stuff works fine. Oh, we're still panicking because that's still. I was worried there for a moment. But you can see we're still getting the correct values, despite the fact that the map is having to reallocate, create new buckets, and then rehash stuff and shove it around. And this is all being compiled with UBSAN and ASAN. So the biggest annoyance with all of this has to have been the fact that C really likes using integers for stuff. I32 everywhere. It's horrible. For example, for the list, our len and capacity are usize, which means they're the size of the native system pointer, right? So it could conceivably point to any value. If you were to fill up system memory completely with bytes, with an array of bytes, you could address any one of them, right? And you can't have a negative address, stuff like that. But stuff like printf, when you want to print out a specific subsection of string, because our string is length delimited, not null delimited, because it's a growable list internally, we have to cast that usize to an int, because printf wants an int, and it's annoying. Now it's cool. We're going to talk about the printing now. Varargs, like, they're just like don't exist. They do exist, but they don't. If you use vararg functions, you basically have type erasure, and it's that's why printf doesn't have any compile time checking. Compilers just have their own we're just gonna, you tell us this is a printf like function, and then we're gonna check it. But the library itself will just screw up if you just don't tell it, give it the information that you told it you were going to give it. But you see, we have type safe printing, and this uses function overloading again, and a really horrible macro hack. So the problem with macros is that if you have a vararg macro, you don't quite know how many varargs you have. You can't just run a function with each vararg being the argument. Except you kind of can. So here's our print header. We have a bunch of format functions. Each format function takes in the self and a file stream. And this means that we do have a way to format strings in memory using open memstring. And this uses statement expressions, one of those GNU C extensions. So we have a bunch of format functions. So that's our function overloading, right? So there's our type safety. Each printable type has a format function which can take it and a file stream, and then that function knows how to print that type. So at that point now we're down to how do we take a bunch of varargs in a macro, so we still have our types, right? Because if we have a function, we have type erasure. So we have our macro, we have all our varargs. How do we run this function for each entry on our varargs? You can't quite, but you kind of can. We have this header. It's underscored. You open it, it says do not edit. It was generated. This is a bunch of automatically generated implementations of print to file underscore and then the number of arguments it accepts. This goes up to 32, but by changing one value and regenerating this, you can have as many as you want. This works using a really, really, really horrible hack that is absolutely hilarious, and it's the fact that the way that varargs, I don't even fully understand it because the syntax for the C preprocessor is so convoluted. I still don't fully understand it. I've modified it, I've edited it, I've written a program that generates it. It's still just like slightly weird. But the way that varargs, when you have a function, when you have a function like macro, which takes varargs, and then you pass the varargs to another function, to another macro-like function, the way that it expands can let you I don't say evaluate, expand to a numerical literal representing the number of varargs that you have. And right here is one of our GNU-C extensions. This lets me handle no varargs to get 0. So what we have is our print, and we take our varargs, and we do this counting, and then we end up going through this chain down to the point that we have a count, and we can call this prefix and then suffix at the end, the count, and that calls the correct macro. And we pass in our varargs, and they expand in the arguments, and we get our printing. And that is generated with this little Python script here. And I can change this to 2, and I can run that, and you can see we can change the number of arguments, our max number of arguments. And then I can just pipe that into xclip. This is a alias for xclip that I have. And then I can just come in here, paste it in, and we can have any number of these, any max number of these we want. It's a really horrible hack. And I would much prefer to be able to do stuff like this, right? And have that be checked at compile time. But you get what you can take, because like now this would have to be that, right? And you have to remember like spaces, and then like when you're quoting something, it looks really weird. But it's better than printf, and I wanted to see how far I could go with using this, like not using IO streams and stuff like that, right? This was pretty fun to build. I would not use it for, well, actually no, I don't know. I don't know if I might. No, probably not. Because of the GNU-C extensions and C++ features, that for the most part ties you to GCC and Clang. Now I've been building here with Clang. Let's change the map default back to 32. I've been building with Clang here. We have our script here. And it requires a lot of... I'm compiling with like a bunch of warnings enabled. Fun fact: GCC doesn't support a lot of these. But I can change that to G++. We can compile and run. and it works. So it works with both of those. GCC was honestly more of a pain to get working with this than Clang, because a lot of this stuff, like GCC doesn't understand this, so it warns you about that. It doesn't understand this, so it warns you about statement expressions and stuff like that. So like, if we come back over to our string, no, our print. Oh, it's not complaining about that one. Hold on. But it complained here. Yeah, I don't know. Oh, I haven't showed. Oh, probably just because I haven't tested it with GCC, but it'll actually complain. But we can show off in memory formatting. So if I go, right. So imagine we have a string here, and I have stir and mut stir. Where's it? Stir mut. No, it's mut stir. As aliases for char to pointer and const char to pointer. Well, this one here is const char to pointer, because like you could put them in here and it would work, but if you put const char pointer in here, you're gonna get an invalid identifier at the end. But we can go string format dead equals format. And we say hello there, and then name. How are you? By the way, here is a bool. And we should actually give that a destructor, and we can print that out. And it's going to yell at me because I haven't taken the address of that. Here we go, and then we can run that. And it's going to yell at me because it's GCC. Here we go. Yeah, you see, it doesn't understand those, so I would have to come over here and fix that now. There we go. So we can format in memory, which is very helpful. Like here, you could just like take this, put it here, and now you've avoided an allocation. But it's a contrived example. So this was really fun to make. Like I said, this is experimentation for some other stuff I'm working on, just to like see where you can get with an API, depending on like what tools you have available to you. I'm quite proud of like how genuinely like comfortable this is to use, as long as you like use it correctly. Yeah. But then again, if you're like building actual stuff, it's better to be a pragmatist and like use templates and stuff if you want to go the C style language route, and like if you want to use C or C++ to build something, then it'd be better to use templates and such. But this was fun to like see how close I can get with just C. Not very close, as these can attest. That's about it. Thanks for watching.